January 17, 1991, 2:51 a.m. local time. An F-117 Nighthawk swept across the Iraqi border at 25,000 feet, invisible to every radar system scanning the darkness below. In the weapons bay, two GBU-27 Paveway III laser-guided bombs hung beneath the black fuselage, each weighing 2,000 pounds and fitted with a BLU-109 penetrating warhead specifically engineered to defeat reinforced concrete. The pilot checked his inertial navigation system one final time, confirmed the targeting coordinates, and began his approach toward the Nukaib Air Defense Coordination Center. Iraqi commanders inside the hardened bunker believed themselves safe. They had spent years constructing multi-layered defenses, thick concrete walls, buried construction, redundant communications, overlapping radar coverage, and surface-to-air missile batteries positioned in concentric rings around every critical facility. Soviet advisors had assured them that depth and mass provided absolute protection against aerial bombardment. Yet in 18 seconds, both assumptions would be proven catastrophically wrong. The pilot opened his bomb bay, acquired the designated laser reflection point transmitted from the targeting system locked onto the bunker's ventilation shaft, released the first GBU-27, and watched as the weapon's guidance fins adjusted in real time, steering toward the invisible beam of reflected laser energy that marked the precise point of impact. The bomb did not strike the roof. It did not crater the surrounding earth. It slipped through a 6-foot-wide opening in the structure's exterior, penetrated deep into the facility, and detonated inside the command center itself, killing everyone within and severing the entire southern air defense network in a single strike. Minutes later, a second F-117 destroyed the other half of the facility. Iraqi forces across the region suddenly found themselves blind, unable to coordinate responses, and completely unaware of what had just happened. They had believed concrete made them invulnerable. They discovered too late that precision made concrete irrelevant. For decades, strategic bombing doctrine had been built on the assumption that destroying hardened targets required overwhelming force. During World War II, Allied bombers dropped hundreds of tons of ordnance on single factories, bridges, and rail yards, accepting that only a small percentage would strike within effective range of the aim point. The United States Army Air Forces concluded after extensive analysis that unguided gravity bombs released from high altitude under combat conditions landed an average of 447 feet from their intended targets. Destroying a reinforced bridge required dozens of aircraft, hundreds of bombs, and multiple sorties, often with no guarantee of success. Losses were severe, accuracy was abysmal, and mission effectiveness depended on saturation rather than precision. Enemy commanders learned quickly that if they could bury their headquarters, harden their bunkers, and reinforce critical infrastructure with enough concrete and earth, they could survive even the most intense aerial campaigns. This calculus held firm through Korea and into the early years of Vietnam, where American pilots discovered that conventional bombing remained as imprecise and wasteful as it had been 20 years earlier. North Vietnamese engineers understood this vulnerability intimately. They constructed the Than Hoa Bridge 70 miles south of Hanoi with deliberate overengineering. Massive steel trusses, thick concrete piers sunk deep into the riverbed, and redundant structural supports designed to absorb direct hits without collapsing. Surrounding the bridge, they positioned anti-aircraft artillery, surface-to-air missile batteries, and early warning radar systems that made every approach a gauntlet of fire. Between April 1965 and May 1972, U.S. Air Force and Navy pilots flew 871 sorties against the Dragon's Jaw, dropping thousands of tons of unguided ordnance in repeated attempts to sever the span. 11 aircraft were shot down, dozens more were damaged. The bridge remained standing, a symbol of American impotence and North Vietnamese resilience. Hanoi celebrated each failed raid as proof that determination and engineering could defeat technological superiority. Yet they failed to recognize that failure was driving innovation at a pace they could not match. In 1964, Texas Instruments began work on a project so simple in concept and so radical in execution that it would rewrite the physics of aerial bombardment. The idea emerged from a straightforward observation. Bombs missed their targets because they had no way to correct their flight path after release. Once a pilot dropped an unguided weapon, its trajectory was fixed by velocity, altitude, wind, and gravity. No amount of skill could compensate for atmospheric variables, aircraft movement, or minor targeting errors. Engineers proposed fitting standard gravity bombs with a guidance kit that included a laser seeker head, control surfaces, and a logic unit capable of detecting reflected laser energy and steering the weapon toward the source. The challenge was not theoretical elegance but practical engineering. The system had to be cheap enough for mass production, rugged enough to survive high-G release forces, and simple enough that existing aircraft could employ it without major modifications. Texas Instruments built the first prototype using an M117 bomb body fitted with aerodynamic canards on the nose and a laser receiver that tracked reflected infrared energy at a specific coded frequency. In April 1965, the first test drop demonstrated that a bomb released from altitude could follow a laser spot painted on the ground and strike within feet of the designated point. The implications were immediately clear. A single aircraft equipped with a laser designator could guide a bomb directly onto a target with accuracy previously unimaginable. The U.S. Air Force authorized Project 3169 in January 1967 as the formal engineering program for development of precision-guided munitions, setting an extraordinarily aggressive timeline. Operational deployment in Vietnam within 1 year. Flight testing began in November at Eglin Air Force Base under the direction of the Paveway Task Force, an interagency organization that consolidated development, testing, and tactical evaluation. The program included 3 divisions. Paveway 1, the laser-guided munitions that would ultimately enter production. Paveway 2, an electro-optical television-guided bomb developed by Rockwell International and designated Hobo. And Paveway 3, an infrared homing system that never reached deployment. By early 1968, Paveway I laser-guided bombs were ready for combat testing in Southeast Asia. The operational concept required 2 aircraft working in tandem. The lead aircraft, equipped with a laser designator pod or handheld device operated by the weapons systems officer, would identify the target and illuminate it with a pulsed infrared laser beam invisible to the naked eye. The wingman carrying Paveway-equipped bombs would release his weapons while the designator aircraft kept the laser locked onto the target. The laser energy reflected off the target surface, creating a cone of infrared light that the bomb seeker head could detect and follow. Guidance fins on the nose adjusted continuously, steering the weapon through the air along an arc that terminated precisely at the laser reflection point. Early tests in Vietnam confirmed that the system worked far beyond expectations. Paveway-equipped F-4 Phantoms struck individual gun emplacements, ammunition depots, and fortified positions with meter-level accuracy, destroying targets that had previously required multiple sorties and hundreds of bombs. Pilots who had grown accustomed to seeing their ordnance scatter across wide impact zones watched in astonishment as 2,000-pound bombs threaded through narrow openings, struck specific corners of buildings, and detonated inside structures rather than around them. Between 1972 and 1973, U.S. Air Force assessments determined that 48% of Paveway laser-guided bombs dropped around Hanoi and Haiphong achieved direct hits, compared with 5.5% of unguided bombs dropped on the same targets during earlier phases of the war. The average Paveway landed within 23 feet of its designated aim point. The average gravity bomb landed 447 feet away. The technological leap represented more than incremental improvement. It was a fundamental transformation in the relationship between aircraft, weapons, and targets. For the first time in the history of aerial warfare, a pilot could guarantee that his bomb would strike exactly where he intended, provided the laser remained locked and atmospheric conditions permitted guidance. North Vietnamese commanders did not grasp what had changed until it was far too late. On May 13, 1972, 14 Air Force jets approached the Than Hoa Bridge armed with Paveway laser-guided bombs. For years, the Dragon's Jaw had absorbed punishment without failing. Its engineers had designed the structure to withstand near misses, partial hits, and even direct impacts from conventional ordnance, relying on redundancy and over-engineering to maintain structural integrity. The Paveway strikes did not scatter across the river or crater the surrounding landscape. They struck the bridge's critical load-bearing points with surgical precision, targeting joints, supports, and stress concentrations that unguided bombs could never reliably hit. The western span collapsed into the Red River. The eastern section sagged, twisted, and became impassable. A bridge that had survived 871 previous sorties fell to 14 aircraft in a single raid. The psychological impact on Hanoi's leadership was immediate and profound. If the Americans could destroy the Dragon's Jaw, no structure in North Vietnam was safe. Soviet advisors scrambled to understand how guidance technology had advanced so rapidly, but the technical details remained classified and the operational implications were undeniable. Precision had replaced mass as the currency of air power. The North Vietnamese had built their defensive strategy on the assumption that hardened targets were survivable. Laser-guided bombs invalidated that assumption entirely. A bunker with 10-foot-thick concrete walls was no more secure than an open trench if a 2,000-pound bomb could be steered through its access tunnel, ventilation shaft, or main entrance. Depth provided no protection against a weapon that could follow a laser beam directly to the target's most vulnerable point. In the final months of the Vietnam War, American pilots struck fuel depots, radar installations, command bunkers, and ammunition storage facilities with near impunity, demonstrating that the era of sanctuary through fortification had ended. Yet the true potential of laser-guided munitions would not be fully realized until technology converged with stealth. Throughout the 1970s and 1980s, the U.S. Air Force refined paveway guidance systems through successive iterations. Paveway II introduced improved aerodynamics, better seeker sensitivity, and compatibility with a wider range of bomb bodies, including the 500-pound Mk-82, the 1,000-pound Mk-83, and the 2,000-pound Mk-84. Paveway III incorporated an autopilot and a more sophisticated guidance section that allowed bombs to glide toward targets from greater distances, expanding the launch envelope and reducing the time aircraft had to remain exposed near heavily defended areas. Engineers developed the BLU-109 penetrating warhead, a specialized bomb body built with a hardened steel case designed to punch through reinforced concrete before detonating, maximizing damage inside buried facilities. These weapons became the GBU-24 and GBU-27 series, laser-guided penetrators capable of defeating bunkers that conventional bombs could not touch. But delivering these weapons over Baghdad, Moscow, or any heavily defended strategic target required an aircraft that could penetrate layered air defenses without being detected, tracked, or engaged. That aircraft was the F-117 Nighthawk, the world's first operational stealth attack platform, a faceted black jet with radar cross-section characteristics so low that it appeared on enemy radar screens as little more than background noise or a flock of birds. The F-117 carried no defensive countermeasures, no radar warning receivers, and no electronic jamming equipment because its primary defense was invisibility. Its weapons bay held two bombs, typically GBU-10 Paveway IIs or GBU-27 Paveway IIIs, and its infrared targeting system allowed the pilot to acquire targets, designate laser aim points, and release weapons without breaking stealth profile. When Iraq invaded Kuwait in August 1990, Saddam Hussein inherited a military infrastructure built on Soviet doctrine and equipped with Soviet-designed defenses. Iraqi engineers had constructed deeply buried command centers beneath Baghdad, reinforced with layer upon layer of concrete and protected by overlapping surface-to-air missile batteries, anti-aircraft artillery, and early warning radar networks supplied by the Soviet Union, France, and China. These bunkers housed communication nodes, intelligence coordination centers, air defense command posts, and leadership facilities that Saddam believed were impervious to aerial attack. He had watched the United States struggle in Vietnam, observed Soviet assessments of American air power, and concluded that static defenses combined with redundant infrastructure would allow Iraq to absorb punishment and sustain command and control even under sustained bombardment. His advisors assured him that American pilots would not dare strike downtown Baghdad, that civilian casualties would erode international support, and that even if strikes were attempted, Iraqi air defenses would exact prohibitive losses. Saddam miscalculated on every assumption. Operation Desert Storm commenced at 2:51 a.m. On January 17, 1991, with an F-117 strike on the Nukaib Air Defense Center, followed minutes later by a coordinated assault on Baghdad's command infrastructure executed by 10 Nighthawks flying singleship missions through the heart of Iraqi airspace. The pilots flew without escort, without jamming support, and without fear of detection because Iraqi radar operators could not see them. Surface-to-air missile batteries fired blindly into the sky, filling the night with streams of tracers and exploding warheads, but the Iraqi gunners had no targets to track. They were shooting at ghosts. F-117 pilots positioned their crosshairs on telecommunications centers, air defense headquarters, intelligence facilities, and leadership bunkers, released their GBU-27 penetrators, and watched as the weapons guided smoothly toward their laser-designated aim points. The bombs did not simply crater roofs or collapse surface structures. They penetrated through ventilation shafts, access tunnels, elevator shafts, and doorways, striking deep inside facilities and detonating in the exact locations where command personnel believed themselves safe. Gun camera footage from the first night of the war captured images that would dominate global media coverage for weeks. Precision weapons dropping through narrow apertures, secondary explosions venting from bunker air shafts, entire buildings collapsing inward as structural supports failed. Iraqi commanders who had spent years preparing for carpet bombing and attrition warfare found themselves facing surgical strikes that decapitated command nodes faster than they could reestablish communications. The Iraqi military operated under a centralized Soviet-style command structure in which field units required authorization from Baghdad for nearly every significant action. When F-117s destroyed the central command bunkers, telephone exchanges, and radio relay stations that linked Saddam's leadership to forward forces, Iraqi divisions lost the ability to coordinate maneuvers, respond to changing battlefield conditions, or even confirm orders. Frontline officers 375 miles from Baghdad sat in fortified positions waiting for instructions that never came, because the infrastructure that transmitted those instructions no longer existed. American strike planners understood this vulnerability intimately. They had studied Soviet doctrine for decades, analyzed Iraqi command procedures during the Iran-Iraq War, and identified the exact nodes whose destruction would paralyze the entire system. Laser-guided bombs allowed them to execute a decapitation strategy with speed and precision that would have been impossible using conventional munitions. A single F-117, armed with two GBU-27s, could accomplish what would have required an entire bomber wing, dropping hundreds of unguided weapons. And it could do so without inflicting the mass civilian casualties that unguided bombing inevitably produced. One of the most dramatic demonstrations of laser-guided precision occurred on February 8, 1991, when an F-117 struck Bunker 2 at the Al-Muthana State Enterprise, a chemical weapons production and storage facility northwest of Baghdad. Intelligence assessments indicated that the bunker contained over 1,122 rockets filled with sarin nerve agent, leftovers from Iraq's war with Iran that had been stored in a heavily reinforced concrete structure designed to survive conventional bombing. The pilot positioned his aircraft over the target, activated his infrared targeting system, locked the laser designator onto the bunker's roof access point, and released a single GBU-27. Gun camera photography confirmed penetration. The bomb punched through the reinforced concrete roof, detonated inside the bunker, and ignited an intense fire that consumed the rockets, chemical agents, and packing materials within. External damage appeared minor, but UNSCOM inspectors who later examined the site confirmed that everything inside had been incinerated. The precision was so exact that the strike left adjacent facilities untouched, demonstrating that American forces could destroy high-value chemical weapons targets without dispersing agents across the surrounding area or endangering nearby populations. Iraqi officials had believed that burying sarin-filled munitions beneath concrete would render them immune to attack. They learned instead that laser guidance could find the weakest structural point and deliver a penetrating warhead exactly where it needed to go. Not all laser-guided strikes achieved perfect results, and the technology had limitations that pilots quickly learned to respect. Laser designation required line of sight between the designator and the target, meaning that smoke, dust, clouds, or atmospheric haze could scatter the laser beam and degrade guidance accuracy. In Vietnam, monsoon weather had frequently forced cancellation of paveway missions, and in the Persian Gulf, smoke from burning oil wells occasionally obscured targets and prevented effective designation. Additionally, early paveway systems lacked the ability to engage targets through cloud cover, requiring pilots to operate in visual meteorological conditions or use infrared targeting systems that could penetrate limited obscuration. The bombs themselves had to be released within specific parameters of altitude, airspeed, and distance from the target to ensure that the seeker head had sufficient time to acquire the laser energy and steer toward it. Too close, and the bomb would not have time to correct its trajectory. Too far, and atmospheric conditions or laser scatter might prevent acquisition. Pilots learned to time their releases precisely, coordinating with weapons systems officers or forward air controllers who maintained laser lock throughout the weapon's flight. Despite these constraints, the operational effectiveness of laser-guided bombs far exceeded any previous precision weapon system. During Desert Storm, F-111 Aardvarks employed GBU-12 Paveway IIs to destroy over 150 Iraqi armored vehicles in night raids during the final weeks of the war, striking individual tanks, armored personnel carriers, and artillery pieces with accuracy that rendered concealment nearly useless. F-117s used GBU-27s to obliterate hardened aircraft shelters, destroying Iraqi fighters trapped inside reinforced hangars that were supposed to protect them from aerial bombardment. One incident illustrated the penetrating power of these weapons with grim clarity. Iraqi air defense personnel at H-2 Airbase watched an F-117 strike their hardened aircraft shelters with GBU-10 Paveway IIs, lighter weapons that lacked the penetrating capability of the BLU-109 warhead. The bombs struck the reinforced concrete roofs and bounced off, leaving the structures intact. Iraqi commanders interpreted this as a defensive success and immediately crammed the shelters full of aircraft, believing they had found a weakness in American precision weapons. They were mistaken. The F-117s returned several nights later carrying GBU-27 penetrators, weapons specifically designed to defeat hardened concrete. The pilots restruck the same shelters, and this time the bombs did not bounce. They punched through the roofs, detonated inside, and incinerated every aircraft packed into the supposedly safe hangars. Iraqi overconfidence had turned protective structures into mass graves for their air force. The lesson was unambiguous. Depth, thickness, and reinforcement provided no sanctuary against weapons that could be steered with meter-level precision and armed with penetrating warheads engineered to defeat exactly those defenses. The GBU-28, nicknamed Deep Throat by its developers, represented the ultimate expression of bunker-penetrating technology. Designed in response to intelligence reports that Saddam Hussein and senior Iraqi leadership were sheltering in deeply buried command bunkers that existing weapons could not reach, the GBU-28 was a 5,000-pound laser-guided bomb built around a modified 8-inch artillery barrel taken from deactivated M110 howitzers. Engineers at the Watervliet Arsenal and Texas Instruments worked under extraordinary time pressure, completing development from initial concept to operational weapon in just 12 weeks. The bomb underwent a single live test drop at the Tonopah Test Range in Nevada, where it demonstrated the ability to penetrate over 100 feet of earth or 20 feet of solid reinforced concrete. The weapon was immediately cleared for combat use and flown to Saudi Arabia aboard transport aircraft. On February 27, 1991, the final day of the ground war, two F-111F aircraft struck a deeply buried command and control bunker suspected of housing senior Iraqi military officials. The first aircraft missed. The second achieved a direct hit. Post-strike reconnaissance imagery showed smoke pouring from the bunker's air vents, indicating that the GBU-28 had penetrated deep into the structure and detonated inside, a testament to the weapon's ability to defeat defenses that had been considered impervious just months earlier. Although only two GBU-28s were dropped during Desert Storm, their existence and demonstrated capability sent a clear message to adversaries worldwide. No bunker, no matter how deep or how heavily reinforced, could provide absolute protection against American precision weapons. The strategic implications extended far beyond individual strikes. For decades, Soviet military doctrine had emphasized hardened command posts, redundant communication networks, and deeply buried facilities as the foundation of survivable command and control. The assumption was that strategic depth, physical protection, and redundancy would allow leadership to continue directing forces even under nuclear attack. Laser-guided penetrators undermined this entire framework. If a conventional bomb could be delivered through a ventilation shaft, access tunnel, or other structural vulnerability with near certainty, then even the most heavily fortified bunker became a potential death trap rather than a sanctuary. Soviet analysts studying the Gulf War recognized immediately that their own command bunkers, designed according to the same principles as Iraqi facilities, were equally vulnerable. The confidence that had underpinned Warsaw-packed defensive planning for decades evaporated in the face of footage showing American bombs slipping through narrow openings and destroying targets from the inside out. Russian military journals published extensive analyses of Desert Storm, focusing particularly on the effectiveness of stealth aircraft combined with precision-guided munitions, and concluded that the technological gap between NATO and Soviet forces had widened to a degree that could not be closed through incremental improvements. The psychological impact was as significant as the tactical one. Iraqi commanders who survived the war reported that the relentless precision of American strikes created an atmosphere of paranoia and helplessness. Officers who had believed themselves safe in bunkers discovered that concrete offered no protection. Tank crews who dispersed and camouflaged their vehicles learned that thermal targeting systems and laser-guided bombs could find them anyway. Air defense operators who fired surface-to-air missiles blindly into the sky realized they were shooting at aircraft they could not see, track, or engage. The doctrine of static defense, deeply rooted in Soviet military theory and adopted by client states worldwide, collapsed under the weight of precision. If you appreciate discovering the Cold War technologies and modern warfare breakthroughs that redefined global power, consider subscribing for future episodes exploring the classified systems that changed history. Forward air controllers, both airborne and ground-based, played a critical role in maximizing the effectiveness of laser-guided weapons. In Vietnam, forward air controllers operating from O-2 Skymaster or OV-10 Bronco observation aircraft would locate targets, mark them with smoke rockets or laser designators, and coordinate strikes by Pavui-equipped fighters. The FAC acted as the eyes of the strike package, maintaining situational awareness, confirming target identification, and ensuring that bombs struck intended objectives rather than friendly forces or civilian structures. The introduction of the Pave Knife laser designator pod in the early 1970s allowed lead aircraft in a strike formation to designate targets, while wingmen dropped their bombs simultaneously, enabling multiple weapons to guide on a single laser spot. This technique dramatically increased the number of bombs that could be brought to bear on a single target in one pass, reducing exposure time and improving efficiency. By the time of Desert Storm, airborne laser designation had evolved into a highly refined process. F-15E Strike Eagles equipped with LANTIRN targeting pods could acquire, designate, and strike multiple targets in a single sortie, switching laser codes between weapons to ensure each bomb tracked its designated aim point. Ground-based special operations forces infiltrated deep into Iraqi territory carrying portable laser designators, identifying high-value targets such as mobile Scud launchers, radar installations, and command posts that satellite reconnaissance could not locate or track in real time. These operators would establish concealed observation positions, acquire targets with thermal optics, illuminate them with coded laser pulses, and guide strike aircraft to precise impact points, often coordinating multiple strikes in rapid succession. The integration of ground-based designation with airborne precision weapons created a kill chain that was faster, more flexible, and more lethal than any previous system, allowing coalition forces to engage time-sensitive targets that would have escaped destruction under traditional bombing methods. The evolution from Vietnam-era Paveway I to Gulf War-era Paveway III represented continuous refinement driven by combat experience and technological advancement. Early laser-guided bombs required near-ideal conditions: clear weather, stable designator lock, and precise release parameters. Paveway II introduced improved aerodynamics through the use of pop-out wings that extended after release, increasing glide range and allowing pilots to launch from greater distances and higher altitudes, improving survivability against air defenses. The guidance section became more sensitive, capable of detecting weaker laser reflections and maintaining lock through light smoke or haze. Paveway III incorporated a digital autopilot that allowed the bomb to fly a more complex trajectory, including the ability to loft upward after release before diving onto the target, further extending range and providing attack angles that were difficult for defenders to predict or counter. The seeker head became more resistant to laser jamming, able to distinguish between the correct coded laser pulse and attempts to spoof or saturate the guidance system with false signals. By 1991, the Paveway family had matured into a family of weapons that could be employed in a wide range of conditions, against targets from lightly constructed buildings to deeply buried bunkers, with reliability and accuracy that made them the weapon of choice for any high-value target. Production numbers reflected operational demand. During Desert Storm, U.S. forces expended approximately 7,400 tons of precision-guided munitions, roughly 90% of which were delivered by Air Force aircraft. The majority were laser-guided bombs from the Paveway series. F-111 Aardvarks, Fe Strike Eagles, F-117 Nighthawks, and F-16 Fighting Falcons all employed Paveways extensively, demonstrating that precision was not limited to specialized platforms but had become integral to air power across the entire strike force. Bridge interdiction provided another vivid demonstration of laser-guided effectiveness. During Desert Storm, coalition forces targeted Iraqi bridges to isolate battlefield sectors, prevent reinforcement, and disrupt logistics. CNA analysis calculated that laser-guided bombs achieved a 60% hit rate against bridge targets, compared to fewer than 1 in 14 unguided bombs hitting similar structures. This represented more than improved accuracy. It meant that a single pair of F-15Es could destroy a critical bridge in one sortie, whereas conventional bombing would have required dozens of aircraft, hundreds of bombs, and multiple days of sustained attack. The economic and operational efficiency was staggering. Each paveway guidance kit cost approximately $25,000 in 1990 dollars, a trivial sum compared to the cost of the aircraft, fuel, tanker support, and aircrew training required to deliver unguided ordnance in the quantities necessary to achieve equivalent effects. The calculus became even more favorable when factoring in reduced exposure to enemy defenses. An aircraft that could strike a target in a single pass and immediately egress faced far lower risk than one that had to make repeated passes or loiter in a defended area waiting for bomb damage assessment. Precision translated directly into survivability, and survivability meant more aircraft and pilots available for subsequent missions. Iraqi planners had assumed that attrition would work in their favor, that coalition forces would lose aircraft faster than they could sustain operations, and that international will would erode as casualties mounted. They failed to anticipate that precision weapons would enable strike rates and effectiveness levels that rendered attrition irrelevant. Coalition forces flew over 100,000 sorties during Desert Storm and lost a total of 75 aircraft to all causes, the majority to ground fire and surface-to-air missiles rather than air-to-air combat. The loss rate was so low that it shocked military analysts worldwide and forced a fundamental reassessment of air power survivability in high-threat environments. Psychological operations reinforced the impact of precision strikes. Early in the air campaign, coalition forces released video footage of laser-guided bombs striking targets with pinpoint accuracy, weapons descending through building ventilation shafts, penetrating bunker entrances, and striking vehicle targets with direct hits. The footage was broadcast globally, reaching not only international audiences but also Iraqi military personnel who watched in horror as the weapons they believed could be evaded or defended against proved capable of finding and destroying targets with near certainty. The videos were intentionally clinical, showing the weapon's eye view as it guided toward impact, emphasizing the inevitability of precision. Iraqi officers who saw the footage understood immediately that dispersal, camouflage, and fortification provided no reliable defense. If an American targeting pod could acquire a thermal signature or a laser designator could lock onto a vehicle, that vehicle was already destroyed, regardless of where it hid or how deeply it was dug in. The psychological effect was profound. Units began surrendering en masse during the ground war, citing the relentless and inescapable nature of coalition airstrikes as a primary reason for their decision to abandon resistance. Captured Iraqi soldiers reported that the constant threat of precision attack made movement impossible, resupply untenable, and morale unsustainable. They described nights spent listening to the distant hum of aircraft engines, knowing that at any moment a bomb might strike their position with no warning, no chance of evasion, and no possibility of defense. This was not the attritional warfare they had been trained for. It was systematic dismantlement. The success of laser-guided weapons in Desert Storm validated decades of investment in precision-guided munitions and fundamentally altered defense planning worldwide. Nations that had relied on Soviet-style mass and depth as deterrents recognized that those strategies were obsolete. New defense architectures emphasized mobility, dispersion, camouflage, and electronic warfare rather than static fortification. Air defense networks began incorporating more sophisticated early warning systems, netted radar coverage, and mobile missile batteries designed to engage and relocate before counter-battery fire could destroy them. Yet even these adaptations struggled to counter the combination of stealth and precision. An aircraft that could not be reliably detected rendered radar networks ineffective. Precision weapons that could strike mobile targets within minutes of detection made mobility alone insufficient. The only reliable defense was to avoid engagement entirely, to hide assets so thoroughly that they could not be found, or to operate in environments where weather, terrain, or political constraints limited American freedom of action. For adversaries contemplating conflict with the United States, Desert Storm established a new baseline of expectations. American air power could find you, strike you with precision, and destroy you before you understood what was happening, and no amount of concrete depth or fortification would change that calculus. The integration of GPS guidance in subsequent years would further expand precision capabilities, creating dual-mode weapons that combine laser designation with satellite navigation for all-weather beyond line-of-sight engagement. Enhanced paveway variants incorporated inertial navigation systems with GPS receivers as backup guidance, allowing bombs to continue tracking toward target coordinates even if laser designation was lost due to smoke, weather, or designator failure. This evolution addressed one of the few remaining limitations of pure laser guidance, enabling strikes in conditions that would have previously forced mission cancellation. By the late 1990s and into the 21st century, precision-guided munitions had become the dominant form of air-delivered ordnance in American and NATO arsenals, relegating unguided bombs to niche roles such as area saturation or training. The transformation that began in the jungles of Vietnam with Paveway culminated in a global air power doctrine built entirely around precision, standoff range, and effects-based targeting. The leap from 447 feet of average miss distance with unguided bombs to 23 feet with early laser-guided weapons, and eventually to under 10 feet with GPS-aided systems, represented more than incremental technical progress. It was a revolution in the nature of aerial warfare itself. Iraqi testimony from the war's aftermath confirmed what strike footage had already demonstrated. Officers who survived the bunker strikes reported that the precision of American weapons created an atmosphere of total vulnerability. One air defense commander described watching coalition aircraft operate with impunity overhead while his missile batteries fired blindly, unable to acquire stable radar locks on targets that appeared as fleeting, indistinct returns if they appeared at all. Tank commanders recounted seeing vehicles beside them explode without warning, destroyed by bombs that struck with such accuracy that adjacent units remained untouched, creating confusion and terror in equal measure. Bunker personnel who emerged after the war described the experience of sheltering in reinforced facilities, believing themselves safe, only to feel the concussion of penetrating warheads detonating deep within structures that were supposed to withstand conventional attack. The survivors spoke of comrades killed in underground command posts, communication centers reduced to rubble despite meters of overhead cover, and the realization that depth was meaningless when weapons could be steered directly to structural vulnerabilities. The Soviet-trained engineers who had designed Iraq's fortifications struggled to comprehend how guidance technology had advanced so far so quickly. They had assumed that laser designation was a marginal improvement over unguided bombs, useful for striking large stationary targets but not capable of the surgical precision demonstrated throughout the war. The reality shattered their models. American laser-guided bombs were not marginally better. They were categorically different, weapons that exploited vulnerabilities rather than relying on blast radius, that found weak points rather than overwhelming defenses through mass, and that rendered traditional fortification strategies not just ineffective but actively counterproductive by concentrating high-value assets in predictable locations. For the United States, the success of precision-guided munitions during Desert Storm validated decades of research, development, and doctrinal evolution that had often been questioned or underfunded. The Paveway program had begun on a shoestring budget in 1964, driven by engineers who believed that simplicity and economy could produce transformative results. Texas Instruments and military planners bet that fitting guidance kits to existing bomb bodies would be cheaper, faster, and more effective than developing entirely new weapon systems, and that operational bet paid off beyond anyone's initial projections. The cost-effectiveness of converting dumb bombs into smart weapons through modular guidance kits meant that precision could be scaled across the entire Air Force inventory without requiring prohibitively expensive specialized munitions. F-16s, F-15s, F-111s, and F-117s could all employ Paveway weapons using compatible designator systems, creating a force-wide capability rather than a niche technology limited to specialized platforms. This scalability proved decisive in Desert Storm, where thousands of precision strikes were executed across a 6-week campaign, something that would have been impossible if precision weapons were rare, expensive, or difficult to employ. The modularity also enabled rapid adaptation. When shortages of GBU-27 penetrators emerged mid-campaign due to unexpectedly high usage rates, F-117 pilots switched to lighter GBU-10s for certain targets, adjusted their tactics, and continued striking high-value objectives without operational pause. When the need for deeper penetration became apparent, the GBU-28 was designed, tested, and deployed in 12 weeks, a timeline unthinkable for traditional weapons programs. The flexibility inherent in the Paveway concept, the ability to make guidance kits with different bomb bodies depending on mission requirements, target characteristics, and availability, created a weapon system that could evolve in real time to meet operational demands. The broader strategic lesson transcended specific weapons or platforms. Desert Storm demonstrated that information dominance, technological superiority, and precision effects could substitute for mass and attrition, that a smaller force equipped with advanced sensors and precision weapons could defeat a numerically larger adversary decisively and with minimal friendly casualties. Iraqi forces fielded over 5,000 tanks, 3,000 artillery pieces, and hundreds of combat aircraft. Coalition ground forces were outnumbered by Iraqi defenders in the Kuwaiti theater at the start of the air campaign. Yet by the time coalition ground forces launched their attack, Iraqi units were shattered, demoralized, and incapable of coordinated resistance. Precision air power had achieved effects traditionally associated with months of ground combat in just over a month of strikes. Commanders who had once measured campaign success in kilometers gained and enemy casualties inflicted began measuring it in nodes destroyed, networks disrupted, and adversary will degraded. The Gulf War marked the transition from industrial age warfare, where victory went to the side that could produce and deploy the most troops, tanks, and artillery, to information age warfare, where victory went to the side that could see first, decide faster, and strike with precision. Laser-guided bombs were the physical manifestation of that transition, weapons that translated information superiority into lethal effects with an efficiency that rendered traditional metrics obsolete. Enemy commanders worldwide absorbed the lessons of Desert Storm and adjusted their strategies accordingly. Nations that had invested heavily in Soviet-style static defenses, massed armor, and centralized command structures began shifting toward mobile forces, distributed command, and asymmetric tactics designed to avoid presenting high-value targets that precision weapons could engage. Non-state actors and insurgent groups recognized that conventional force-on-force engagements against precision-equipped militaries were suicidal and adapted strategies that emphasized dispersion, concealment among civilian populations, and attacks timed to exploit brief windows of vulnerability. The proliferation of man-portable air defense systems, anti-access strategies, and urban warfare techniques reflected an understanding that defeating American air power required avoiding engagement rather than meeting it head-on. Yet even these adaptations struggled against the relentless evolution of precision technology. Laser-guided weapons gave way to GPS-guided JDAMs, which in turn were supplemented by small-diameter bombs, sensor-fused weapons, and eventually loitering munitions and armed drones that could track mobile targets for hours before striking. Each generation of precision weapons narrowed the engagement envelope, reduced response times, and expanded the range of targets that could be prosecuted effectively. The fundamental dynamic established in Vietnam and perfected in the Gulf War, that American forces could find, fix, and destroy high-value targets with near certainty, remained constant even as specific systems and tactics evolved. The humanitarian implications of precision weapons, though often debated, represented a genuine departure from previous eras of strategic bombing. World War I-era area bombing campaigns against German and Japanese cities killed hundreds of thousands of civilians, destroyed vast swathes of urban infrastructure, and were accepted as necessary costs of total war. Korea and Vietnam saw similar patterns, with unguided bombs inflicting collateral damage that eroded public support and international legitimacy. Laser-guided weapons offered an alternative, the ability to strike military targets with minimal damage to surrounding areas, reducing civilian casualties and preserving critical infrastructure. This was not purely humanitarian concern. Precision reduced political costs, maintained coalition cohesion, and preserved post-war stability by limiting destruction to regime and military targets rather than obliterating entire cities. The infamous Ameria shelter bombing, in which an F-117 struck a facility believed to be a military command bunker that turned out to contain Iraqi civilians, illustrated both the potential and the limitations of precision. The weapon struck exactly where it was aimed, penetrating the shelter and destroying its contents with clinical efficiency. The tragedy was not technical but intelligence-driven, a failure of target identification rather than weapon accuracy. This distinction mattered. Precision made intentional discrimination between military and civilian targets possible in ways unguided bombing never could. Whether that potential was realized depended on targeting decisions, intelligence quality, and rules of engagement, but the technical capability existed in a form it never had before. Join us here at Classified Warfare as we uncover the operations, technologies, and doctrines that shifted the balance of power, revealed adversary vulnerabilities, and ensured that in modern warfare there is no place left to hide. When enemy commanders realized that laser-guided weapons could find a doorway from miles above and penetrate defenses they believed impervious, the confidence in static fortification collapsed. Soviet doctrine, Iraqi strategy, and decades of defensive theory were invalidated in 6 weeks of precision strikes that demonstrated beyond doubt that in the age of laser guidance, depth is irrelevant. Concrete is penetrable and sanctuary is an illusion.